You know, I've spent my entire career trying to help people understand the universe. And I've learned that sometimes the cosmos doesn't announce its greatest mysteries with fanfare. It doesn't send a formal invitation. It just appears, flash, a signal, and suddenly everyone's asking questions they never thought to ask before. That's what happened on January 14th, 2025, a day that seemed ordinary in every way. People going about their lives, checking their phones, worried about their daily concerns. But somewhere, billions of light years away, the universe was putting on a show so spectacular, so violent, so energetically extreme that it would eventually capture the attention of scientists around the world. A gamma-ray burst, GRB 250314A, to be precise. 10 seconds of the most intense radiation the cosmos could muster. And here's the thing, within hours the headlines started appearing. Signal from deep space. Mysterious cosmic message. Could this be aliens? The internet did what the internet does. It speculated, it wondered, it imagined possibilities. But let me tell you something. Before we get caught up in the romantic notion of extraterrestrial communication, we need to understand what we're actually looking at. Because the reality, the real story, is far more spectacular than any fiction we could dream up. Let me take you on a journey, not just to that signal, but to understand the cosmos in a way that makes you realize just how absolutely extraordinary this event really is. First, let's talk about scale. And I mean true scale, the kind that makes your brain hurt a little bit when you really sit with it. Our sun. This massive ball of nuclear fusion that's been burning for about 4.5 billion years. It's enormous. If you could hollow it out, you could fit about 1.3 million Earths inside it. 1.3 million. Our entire planet is a grain of sand compared to the sun. And the sun is just average, completely ordinary, medium-sized star in an ordinary galaxy. Nothing special about it whatsoever. It's the cosmic equivalent of a middle manager at an insurance company. Now, imagine a star that's not average. Imagine a star that's 50 times heavier than our sun. Maybe even 100 times. These are monsters, hypergiants. When you look at them in the night sky and you can actually, with telescopes, they just seem wrong somehow. Too bright, too dominant, like they're consuming all the attention in a region of space. These massive stars, they live fast, they burn hard, they die young. A star like our sun will live for about 10 billion years. It'll spend 10 billion years fusing hydrogen into helium, slowly, steadily, reliably. But a star 50 times more massive, it'll be dead in a few million years, maybe a few million. Because when you're that massive, the pressure at your core is so intense, the temperature so extreme, that you burn through your nuclear fuel at a rate that's absolutely frantic. Think of it like this. Imagine two cars. One's a hybrid that gets amazing mileage. It'll run for 20 years on a single tank. The other, a massive V12 gas guzzler. It needs to refuel constantly. It burns through fuel at a rate that seems almost self-destructive. But while it's running, it's powerful. Massive stars are like that cosmic V12. They're bright, they're hot, they're violent, and they're burning through their fuel at a rate that's almost incomprehensible. But here's what happens next. And this is where it gets really interesting. When a massive star reaches the end of its life, and we're talking about millions of years of nuclear fusion finally reaching its limit, something extraordinary happens. The star doesn't just dim and fade away. It doesn't go gently into that good night. Instead, it collapses. All that mass, all that stuff that's been burning and fusing and creating heavier and heavier elements. Suddenly, the nuclear reactions that have been holding it up against gravity for millions of years just stop. They can't sustain themselves anymore. The fuel is gone. The chemistry is exhausted. And when the nuclear reactions stop, there's nothing holding the star up against its own gravity anymore. Imagine you're holding up a massive weight. Your arms are supporting it. You're struggling, you're sweating, you're using every bit of strength you have. But you're holding it. Then suddenly you get tired. Your muscles give out. What happens? The weight falls, crashes down. And it doesn't just fall a little bit. It falls hard. It falls with all the force of gravity acting on something incomprehensibly massive. That's what happens to a star when it dies. The outer layers of the star come crashing inward at speeds that are so fast, so violent, that the temperature at the core reaches temperatures we can barely comprehend. We're talking about billions of degrees. Billions. The core becomes so dense, so compressed, that matter itself starts behaving in ways that violate our everyday intuition. The protons and electrons that normally make up the atoms of material get crushed together. They fuse into neutrons. The matter becomes so compressed that a teaspoon of it would weigh as much as a mountain. Teaspoon. A single teaspoon of neutron star material would weigh billions of tons. But here's the thing. For the most massive stars, the real giants among giants, even neutron star density isn't enough to stop the collapse. The gravity is just too strong. The mass is just too enormous. The collapse continues. And when the collapse passes a certain point, when the density reaches a certain threshold, something extraordinary happens. The matter collapses past the point of no return. The gravity becomes so intense that nothing, not even light itself, can escape. You create an event horizon. And inside that event horizon, you create something that shouldn't exist in any rational universe. A black hole, the ultimate object of destruction. The final resting place of matter that's been compressed beyond all recognition. In many ways, a black hole represents the absolute breaking point of physics itself. But here's where the story takes another turn. And here's where it gets even more spectacular. When a massive star collapses and creates a black hole, it doesn't just create a black hole sitting alone in the void. Usually, and this is absolutely crucial, the dying star has some companion. Sometimes it's another star. Sometimes it's material in a disk around it. There's stuff surrounding this black hole. Stuff that's been attracted by the black hole's gravity. And now you have a situation that's almost incomprehensibly violent. Material is spiraling toward the black hole. It's accelerating. It's heating up. The friction between different layers of material is so intense that it generates temperatures that rival the cores of stars. Maybe hotter. The material is approaching the speed of light. We're talking about matter being accelerated to 99.99% the speed of light. Einstein's relativity starts to matter in a big way. And here's the thing. When matter gets this energetic, when it's moving this fast, with this much kinetic energy concentrated in such a small region, something happens. Magnetic fields get twisted up. The material becomes so energetic that it can't just fall into the black hole peacefully. Instead, some of it, a significant portion of it, gets ejected outward. But not outward in all directions. No, it gets ejected in two jets. Perfect jets. Coherent beams of material and radiation shooting out in opposite directions from the black hole, perpendicular to the accretion disk. These jets are moving at relativistic speeds. 99-point-something% the speed of light, and they're composed of the most energetic material in the universe. Electrons, protons, and photons accelerated to such tremendous energies that when you convert them to energy using Einstein's E=mc² equation, you get numbers that are almost abstract in their immensity. These jets are the universe's most efficient weapons. They're laser-focused beams of pure destruction. And when they're aimed at Earth, or more precisely, when Earth happens to be in the right place to detect them, we see something we call a gamma-ray burst. Now, let me explain gamma rays for a second. Because light, you see, isn't all the same. Our eyes can see visible light, the spectrum of colors from red to violet. But that's just a tiny, tiny fraction of the full electromagnetic spectrum. Beyond visible light, you have infrared. That's heat radiation. We use it in thermal cameras, in night vision goggles. It's electromagnetic radiation with lower energy, longer wavelengths. Then you have microwaves, radio waves. These are even longer wavelengths, even lower energies. And most of the universe communicates in these frequencies. Radio telescopes pick up signals from across space on these wavelengths. But go the other direction, beyond visible light toward shorter wavelengths and higher energies. You get ultraviolet light, then X-rays. And then, at the extreme end of the electromagnetic spectrum, you get gamma rays. Gamma rays are the highest energy photons that exist. A single gamma ray photon carries more energy than millions of visible light photons combined. They're incredibly penetrating. They'll pass right through lead, right through concrete, right through almost anything. In hospitals, we use them to kill cancer cells. They're that energetic, that powerful. When a gamma-ray burst is detected, we're not talking about visible light. We're not talking about something your eyes could see. We're talking about radiation so energetic, so high frequency, that it would be completely invisible to human sight. But it's there. And when satellites designed specifically to detect gamma rays pick it up, they start screaming. Literally, alarms go off. Scientists get called out of meetings because gamma-ray bursts are rare, and they're spectacular. So here's what happened on January 14th. Somewhere, and we now know approximately where, in a distant region of space, this entire process took place. A massive star reached the end of its life, collapsed, created a black hole. Material spiraled toward it. Jets were ejected, and those jets released a burst of gamma rays that was so intense, so energetic, that it lit up space with more energy than our sun will produce in its entire 10 billion year lifetime. All in 10 seconds. The jets of the burst happened to be pointed roughly in our general direction. And the light from that burst light that had been traveling through space for 13 billion years finally reached Earth. When it did, satellites detected it. Specifically, gravitational wave detectors, X-ray observatories, and gamma-ray detectors positioned around the planet all picked up the signal more or less simultaneously. The burst was catalogued as GRB 250314A, and within hours, follow-up observations started. Telescopes around the world, optical telescopes, radio telescopes, infrared detectors, X-ray observatories, all pointed toward the same patch of sky. Scientists started coordinating. Data started being collected. And the physics community started analyzing what had been detected. The distance to the burst was measured using something called redshift. When light travels through the expanding universe, the expansion stretches the wavelengths of the light, making it shift toward the red end of the spectrum. The farther the light has traveled, the more the universe has expanded during its journey, the greater the redshift. By measuring the redshift, astronomers can calculate how far away the source is. And the result? 13 billion light-years. 13 billion light-years away. Let me put that in perspective for you. The universe is about 13.8 billion years old. We're pretty confident in that number. It comes from measurements of the cosmic microwave background, from observing the expansion rate of the universe, from multiple independent lines of evidence all pointing to the same age. 13 billion light-years means the light from this burst has been traveling toward us for 13 billion years, which means we're looking back in time 13 billion years, which means we're seeing an event that occurred when the universe was only about 800 million years old. Think about that for a second. 800 million years into a universe that's now 13.8 billion years old. That's like looking back at human history and looking at a period when our ancestors hadn't even developed language yet. That's ancient. That's ancient by human standards. But by cosmic standards, that's the infancy of the universe. We're talking about a time when galaxies were still forming, when massive stars were popping into existence, when the universe was still young and wild and relatively small. And in that ancient universe, this star lived out its millions of years life cycle, and then it died in the most spectacular way possible. And the light from that death has been traveling toward us ever since. Now, this is where things get interesting in a different way. Because as soon as the news broke, and the internet being what it is, people started asking the question. The question that's always lurking in the background of any unusual cosmic event. Could this be aliens? Could this be a message? And I understand the appeal. I really do. There's something romantic about the idea of an advanced civilization on the other side of the universe trying to reach out, trying to make contact, using some cosmic signal to say hello, to say we're here, we exist, we're intelligent. The problem is, the more you think about it, the more you realize how profoundly impractical that would be. Let's say you're an advanced alien civilization. You've mastered technology beyond our wildest dreams. You've colonized solar systems. You've figured out ways to harness the power of stars. You've developed science at a level that would make our greatest physicists look like children scribbling in the dirt. And you want to send a message to other civilizations in the universe. What do? Do you deliberately trigger a gamma-ray burst? Do you somehow engineer a stellar collapse? Do you create a black hole and manipulate its jets to beam a message across space? Because if that's your choice of communication technology, I have some observations to make. First, you'd need to know exactly where Earth is. Among 2 trillion galaxies, each containing hundreds of billions of stars, we're a small blue planet orbiting an ordinary yellow star in the suburbs of an unremarkable spiral galaxy. Finding us would be like looking for a specific grain of sand on a beach that spans the entire observable universe. Second, you'd need to time it perfectly. You'd have to engineer this burst millions of years in advance, or calculate millions of years in advance, such that the light would arrive at Earth at exactly this moment in history. Not 1,000 years ago, not 1,000 years from now, right now, in 2025. Third, and most importantly, if you're trying to send a message to someone, you don't use the most chaotic, violent, destructive, unpredictable phenomenon in the universe as your postal service. You design something, you engineer it, you make it reliable. You don't say, let's destroy a star and hope the light reaches the right place. It's like the entire civilization, this super advanced, godlike civilization, forgot everything they know about engineering and decided to communicate using nuclear explosions. On purpose, across space. No, if that's their idea of a good message delivery system, they need better engineers, or a better product manager, or both. But here's what I think is actually happening. And here's what's actually fascinating about this event. This isn't a message from aliens, but it's absolutely a message from the universe. And in some ways, it's more profound than anything aliens could tell us. What we're looking at when we study gamma-ray bursts like GRB 250314 is physics at its most extreme. We're looking at a laboratory where the rules of physics are pushed to their absolute breaking point, where matter behaves in ways that violate our everyday intuition, where gravity, relativity, quantum mechanics, electromagnetism, all the fundamental forces of nature, are operating at maximum intensity simultaneously. In our particle accelerators here on Earth, we create conditions of extreme energy. We smash particles together at velocities close to the speed of light. We generate temperatures comparable to the first moments after the Big Bang. And from those experiments, we learn about the fundamental nature of reality. We test our theories. We refine our understanding. But the universe has been conducting these experiments naturally for billions of years. Every gamma-ray burst is a natural laboratory. Every collision of neutron stars is an experiment in extreme physics. Every black hole is a test case for Einstein's equations. And the fact that we can detect these events, the fact that we have the technology, the knowledge, the infrastructure to point our instruments at a distant part of the sky and say, yes, we detected this, we measured this, we can extract data from it, that's something extraordinary in its own right. Think about it. We're a species that evolved on a small planet. We developed language so we could communicate with each other. We developed mathematics so we could describe patterns. We developed science so we could understand how the world works. And then, over the last 100 years or so, we've developed technology that lets us detect the most energetic events happening in the universe billions of light years away. That's not something to take for granted. That's not normal. That's extraordinary. We've built satellites that specifically watch for gamma-ray bursts. The SWIFT satellite, for example, was designed partly to detect these events. When a burst occurs, the satellite can pinpoint its location within seconds. It can send that location to ground-based telescopes around the world. And those telescopes, operated by scientists in different countries, speaking different languages, can coordinate and observe the same event simultaneously. That's international cooperation. That's the accumulated knowledge of humanity being leveraged to understand the cosmos. Here's what GRB 250314A and gamma-ray bursts in general tell us about the universe. First, it tells us that the universe is violent, spectacularly, incomparably violent. We live in a cosmos where matter is being torn apart at cosmic scales, where stars are collapsing into black holes, where jets of radiation are tearing through space at nearly the speed of light. If you think the universe is a peaceful, quiet place, you're looking at only the tiniest fraction of what's actually happening. Second, it tells us that the universe is old. 13 billion light-years is a huge distance, but it's not the maximum distance we can observe. We've observed gamma-ray bursts at 15 billion light-years. We've observed galaxies at even greater distances. The universe is vast in both space and time, and the processes that create these violent events have been happening continuously since not long after the Big Bang. Third, it tells us that the universe is comprehensible. We can measure the distance to a burst using redshift. We can calculate the energy released using the observed radiation. We can infer the physics of black holes and neutron stars from the characteristics of the burst. The universe follows rules. Those rules are comprehensible to human minds. That's not guaranteed. The universe could be fundamentally incomprehensible, but it's not. It's knowable, and that's extraordinary. Fourth, it tells us about the endpoints of stellar evolution. When we study gamma-ray bursts, we're studying what happens at the extreme end of a star's life. We're learning about black holes. We're learning about the conditions around these objects. We're refining our understanding of general relativity. Every burst adds to our knowledge. And fifth, and maybe most profoundly, it tells us about our place in the cosmos. We're observers. We're capable of understanding events that happened billions of years ago, billions of light years away. We've developed the knowledge and technology to participate in the universe's greatest mysteries. That's not alien contact, but it's something pretty special. Now, let me talk about why this particular burst, GRB 25031, got scientists on their toes. First, the duration. 10 seconds is actually on the longer side for a gamma-ray burst. Most bursts last less than 2 seconds, but this one kept going. That tells us something about the mechanism that created it. It suggests a specific type of progenitor, probably a massive star with a binary companion, where material was being transferred from one star to the other before the collapse happened. Second, the distance. 13 billion light-years is far, but not the farthest we've observed. However, at that distance, the fact that we could still detect it tells us something important about the burst's energy. This wasn't a weak burst. This was a truly energetic event. The explosion was so intense that even after 13 billion light-years of travel, diluted across the cosmic expansion, filtered through dust and gas, the radiation was still strong enough for our detectors to pick up. Third, the afterglow. After the initial gamma-ray burst, there's usually an afterglow. The jet continues to interact with the surrounding material, creating X-rays, visible light, infrared radiation. This afterglow can last for days or even weeks. Astronomers use the afterglow to get more precise measurements of the burst's location, its energy, its composition. They can trace the evolution of the jet as it decelerates and brightens. Each burst is unique. Each one teaches us something new. Fourth, the host galaxy. By studying where the burst came from, the location in the sky, astronomers can try to identify the host galaxy. What type of galaxy was it? How bright? What evidence of star formation does it show? These observations tell us about the environments where massive stars are forming and dying in the ancient universe. They tell us about how galaxies evolve over cosmic time. Let me zoom out for a moment and talk about gamma-ray bursts more generally. Because GRB 250314A isn't unique. It's one of thousands that have been detected over the past few decades. And each one has added to our understanding. In the 1960s, the United States military launched satellites called Vela satellites. Ostensibly, they were there to detect nuclear weapons testing in the Soviet Union. They had gamma-ray detectors designed to catch the telltale signature of a nuclear explosion. But something unexpected happened. They started detecting gamma-ray bursts coming from space, from outside Earth's atmosphere. At first, nobody knew what they were. They came from random directions. They had no obvious pattern. They seemed to come from anywhere in the sky at any time. Were they nearby? Were they distant? Were they within our galaxy or beyond it? The debate raged for decades. But finally, in the 1990s, we got an answer. A satellite called Compton, launched by NASA, could detect gamma rays with enough precision to pinpoint their locations. And what we discovered was that gamma-ray bursts were extragalactic. They were coming from beyond our galaxy, from distant galaxies billions of light years away. That was profound. It meant these were the most energetic events in the universe. It meant we were looking at phenomena that dwarfed anything we could create with our most powerful technology. Since then, gamma-ray bursts have become tools. Tools for studying the early universe. Tools for learning about black holes and neutron stars. Tools for understanding extreme physics. When a burst is detected, hundreds of astronomers around the world mobilize. They point their instruments. They collect data. They collaborate. And slowly, we've built up a picture. We understand the progenitors, the objects that create these bursts. We understand the mechanisms. We can predict what the afterglow will look like. We can learn about the composition of the burst, the energy, the dynamics. But every burst is still unique. Every burst still surprises us in some way. And that's what keeps this field exciting. But let me talk about something else too. The cultural moment. Why did GRB 250314A get the attention it did? Why did people on the internet immediately start asking about aliens? Because, fundamentally, we're curious. We're a species that looks up at the night sky and wonders. And we should. That's a good instinct. That's how science begins. With wonder, with questions. And I think there's also something deeper. There's a part of us that's lonely. We're on this planet, surrounded by billions of other humans, connected through technology, and yet many people feel isolated. And when we look out at the universe, at all those stars and galaxies, we think, are we alone? Is there anyone out there? That's not a stupid question. That's a profound question. We don't have a definitive answer yet. We haven't found any evidence of extraterrestrial intelligence. Not yet, but that doesn't mean they're not out there. With 2 trillion galaxies, each with hundreds of billions of stars, the mathematics alone suggests that intelligence could exist somewhere out there. But here's the thing. Even if there's no alien civilization trying to send us a message with this particular gamma-ray burst, that doesn't make the burst any less spectacular. It doesn't make the event any less significant. It just means the message is coming from nature itself, not from an alien intelligence. And nature has a lot to teach us. From studying events like GRB 250314A, here's what we've learned about the cosmos. 1. Black holes are real, not theoretical constructs, real objects that actually exist in the universe. We've inferred their existence from the behavior of objects around them. Gamma-ray bursts provide some of the best evidence for black holes, because the jets they produce are so distinctive, so energetic, that only a black hole could power them. 2. Massive stars end in spectacular fashion. Not all stars explode as supernovae. Many simply collapse into black holes without any visible explosion from Earth's perspective. But when the conditions are right, when there's the right kind of binary companion, when there's the right amount of material, you get a gamma-ray burst. And that's one of the most energetic phenomena in the universe. 3. The universe is a laboratory for extreme physics. In our research institutions, in particle accelerators, we try to recreate extreme conditions to test our physics. But the universe does it naturally, on scales so vast, with energies so tremendous, that it makes our experiments look like child's play. By studying natural phenomena, we're learning more about physics than we ever could from experiments alone. 4. Collaboration works. The detection and follow-up observation of gamma-ray bursts is a global effort. Satellites owned by different countries coordinate. Astronomers across the world share data. Theoretical physicists and observational astronomers work together. Different research groups compete and collaborate. And the result is knowledge that's richer, more complete, more robust than any individual researcher could achieve alone. 5. The universe is comprehensible. We can measure the distance to objects billions of light-years away using the redshift of their light. We can calculate the energy of explosions that happened billions of years ago by analyzing the radiation we detect today. We can infer the physics of objects too extreme to study in the laboratory. The universe follows rules. We can understand those rules. Let me take a moment to appreciate how extraordinary this moment is. From a historical perspective, 100 years ago, we didn't even know that galaxies other than our own existed. The Andromeda Galaxy, our nearest major galactic neighbor, was thought to be a nebula within the Milky Way. In the 1920s, Edwin Hubble observed Cepheid variable stars in Andromeda and showed that they were too distant, too far away to be part of our galaxy. Suddenly, our universe expanded. We weren't in a single galaxy. We were in a universe of galaxies. 50 years ago, we didn't know gamma-ray bursts existed. They were discovered by accident by military satellites watching for nuclear explosions. We didn't understand what they were. We couldn't explain them. 20 years ago, we had just begun to pinpoint the locations of gamma-ray bursts precisely enough to study their afterglows. We were building the models that could explain their progenitors. The field was young. The understanding was primitive by today's standards. Today, we have networks of satellites that specifically hunt for these events. We have rapid follow-up mechanisms that can mobilize telescopes across the globe within minutes of a burst detection. We can measure distances, energies, compositions. We can construct detailed models of the physics involved. And tomorrow will be even better. New satellites are being launched. New detectors are being built. Our understanding will deepen. This is the trajectory of human knowledge. From ignorance to wonder to question to investigation to understanding. And then to deeper questions based on that understanding. Now, let me get a little philosophical for a moment, because this is important. When we detect an event like GRB 250314, when we measure its distance, when we understand its physics, we're participating in something profound. We're extending human knowledge to the farthest reaches of the universe. We're answering questions that seemed impossible just decades ago. But it also puts us in perspective. We're a species on a small planet. We haven't even left our solar system yet. Our greatest space probes have just entered interstellar space. The nearest star system, Alpha Centauri, is 4.5 light-years away. A journey there with current technology would take many tens of thousands of years. And yet, we can look at light that's been traveling for 13 billion years. We can understand the physics of events that happened at distances that seem almost infinite. We can ask questions about the structure of the universe itself. There's something humbling about that, and something empowering. Humbling because it reminds us how small we are. Empowering because it shows us how much our minds can achieve. So what happens now? What's the future of gamma-ray burst astronomy? First, we'll continue to detect and study more bursts. Every burst adds to our dataset. Every burst adds a data point to our understanding of how the universe works. Over time, patterns emerge. Statistical relationships become clearer. Our models get more refined. Second, we'll develop new technology. Next-generation telescopes are being built. Better detectors. More sensitive instruments. The James Webb Space Telescope has already revolutionized our ability to study distant objects. Future telescopes will do even more. Third, we'll combine gamma-ray bursts with other tools. Gravitational wave detectors like LIGO and Virgo are now sensitive enough to detect mergers of neutron stars, which also produce gamma-ray bursts. By combining gravitational wave data with electromagnetic data, we get a richer picture of these events. Multi-messenger astronomy, it's called, and it's revolutionizing how we study the universe. Fourth, we'll search for the signatures of even more extreme events. Perhaps there are phenomena we haven't even discovered yet. Perhaps there are questions we haven't thought to ask. But if history is any guide, the universe will surprise us. And finally, we'll use these events as tools to study fundamental physics. Black holes, quantum gravity, the nature of spacetime itself. These are questions that gamma-ray bursts can help us answer. Every observation is an experiment in extreme conditions. Let me explain a little bit about how we actually detect these bursts, because it's not trivial. It's actually quite remarkable. Gamma rays don't penetrate Earth's atmosphere very well. The atmosphere shields us from them, which is good for biological life on the surface. But it means we can't detect gamma rays from space-based telescopes on the ground. We need satellites. So we've built satellites specifically designed to detect gamma rays. The SWIFT satellite, for example, was launched in 2004. It carries the Burst Alert Telescope, which scans the entire sky. When a gamma-ray burst occurs, the BAT detects it, calculates the location. It sends that location to the spacecraft's autonomous guidance system. and the spacecraft reorients itself to point its more precise telescopes at the burst. This all happens automatically. Within seconds of detecting a burst, Swift can pinpoint its location to within an arc minute, about the size of a small star in the sky. And it sends that location to Earth via radio. Other satellites, ground-based telescopes, they all receive this alert. They point their instruments. The observation begins. And the follow-up observations are crucial, because the initial burst lasts only seconds. But the afterglow, the radiation produced as the jet slams into the surrounding gas, that lasts longer. It starts bright and slowly fades. By observing this afterglow across multiple wavelengths, gamma rays, X-rays, visible light, infrared, radio, we can learn about the composition of the jet, the density of the surrounding material, the distance to the source. Here's something really interesting about gamma ray bursts that many people don't appreciate. The jets are traveling at relativistic speeds, 99-point-something% the speed of light. At these speeds, relativistic effects become crucial. Time dilation, length contraction, relativity of simultaneity, these aren't abstract concepts anymore. They're determining factors in what we observe. For example, because the jet is moving toward us at relativistic speeds, the radiation appears brighter than it would if the jet were stationary. This is called relativistic beaming. It's similar to the Doppler effect for light. When a light source is moving toward you, the light is blue-shifted, compressed into higher frequencies. And the intensity is increased because the relativistic motion is compressing the radiation into a narrower beam. This beaming effect is crucial to understanding gamma ray bursts. Without it, the bursts wouldn't be bright enough to detect from Earth. The jets are incredibly energetic, but they're also incredibly narrow. They're not isotropic, they're not radiating equally in all directions. They're beamed, and that beaming is what makes them detectable across cosmic distances. This is also why gamma ray bursts point toward us. We're only detecting the ones where the jet happens to be pointed roughly in our direction. If we could somehow detect all the gamma ray bursts in the universe, regardless of orientation, we'd see many more of them. The ones we detect are biased toward the ones pointed at us. Another interesting thing about gamma ray bursts is the mechanism by which the radiation is produced. The jet contains energetic particles, electrons and positrons. Mainly, these particles are also moving at relativistic speeds. As they move through magnetic fields, they experience forces that curve their paths. When a charged particle accelerates, it radiates electromagnetic radiation. This process is called synchrotron radiation. At relativistic energies, the radiation produced is hard, high-frequency, gamma rays. It's the same mechanism that's used in synchrotrons here on Earth, particle accelerators, where we deliberately use synchrotron radiation for research. But the universe is also using inverse Compton scattering. That's a process where low-energy photons get scattered by high-energy electrons, and in the collision, the photons gain energy, become higher frequency. It's like a cosmic pool game where electrons hit photons and send them off with more energy than they came in with. So you have multiple radiation mechanisms all operating simultaneously in the jet. Synchrotron radiation producing the bulk of the gamma rays. Inverse Compton scattering boosting the energies further. Bremsstrahlung, the radiation produced when charged particles decelerate. All of these processes contribute to the observed spectrum. And the spectrum, the distribution of radiation across different frequencies, tells us about the physical conditions in the jet. The density of particles, the strength of the magnetic field, the distribution of electron energies. By analyzing the spectrum, we can reconstruct the physics of the jet. Let me tell you what we actually measured from GRB 250314A. These are the actual data points that scientists analyzed to understand the burst. First, the timing. The burst was detected by multiple satellites with overlapping fields of view. By comparing the arrival times at different detectors, we could triangulate the location. Not perfectly, there's always some uncertainty, but well enough to guide follow-up observations.